Thank you to the organizers and for giving me this opportunity to talk here, and thank you everyone for making it to this early morning talk. I know it's not easy. Today I'm going to talk about combinatorial markets, algorithms and applications. This is a joint work with Nikhil Devanur, Jugal Garg, who may be here somewhere in the audience, Vijay Wazirani, and Sadra Yazdanbol. Okay, so this work started with really like an application in mind. So let me start with the application. So this is mainly about the application. This application is about cloud. So we have been using cloud since some years for managing, storing, processing data. And it has been highly successful business model. There are a lot of companies involved in this. And the work our motivation came from the questions from Microsoft. And this market is increasing. It seems at a steady rate of some 19 or 20%. And now currently it's in some billions of dollars, and the projection is it's going to keep increasing. So the basic question, or the basic questions here is that there are virtual machines in clouds. These are remote machines, and users want to use these machines to execute their tasks. They have budget, they have money to spend, and they want to finish their tasks as soon as possible. The task of the service provider is to set prices and decide the allocation. Now here, currently there are many ways this is done. It is either rented, or there are exactly in the market setting where you exactly set prices of the virtual machines and people buy as per their convenience. I'm going to focus on the market setting of it, not the renting part. So this immediately sets up a market, right? But this market is not like a traditional market. In a traditional market, typically you kind of assume that the buyers have some preferences over goods, they come with the money, and then if they go to the market, they buy what they like from the money. Here, they want to execute a set of jobs, and to execute these jobs, they will require some minimum amount of resources. Okay, this constraint is not there in traditional market. So we'll call them covering constraints, and this is kind of unique to this market. And there is no utility, but there is some kind of cost, delay cost in this case. And so the objective is to minimize the delay here for this example. So taking clue from this, we define a market with covering constraints, where there are a set of buyers and set of goods, and these are divisible goods. Every buyer or agent has money to spend, and they have some covering constraints over goods. So they need to buy some minimum amount of goods to satisfy some covering constraints, and we will consider linear covering constraints in this talk. Once we set the prices, the agent will buy a bundle or demand a bundle which minimizes some objective, some cost. It should be within the budget, so the agent should be able to afford the bundle, and it should satisfy all the covering constraints of the agent. Okay. So this is the basic market, and at equilibrium, the market should clear. That means for every good, there should not be any excess demand, so there should not be less good than the demand. And if there is more supply than the demand, then the price of the good should be zero. It is just saying that there is not enough demand for this market, for this good, so it should not be priced at non-zero price. So these are typical market constraints. And it's kind of ensuring efficiency, right? Everybody gets what they like within their budget, and there is no wastage of goods, basically. Whichever good is liked by a lot of agents is not over demanded. Right? Everybody is happy in some sense. The general model is able to not only capture the cloud example that we saw, it can capture many other things. One of them is network flow. So let's say, think of packet routing. You have a network. It could be a road network or internet network, whatever. And there are edges the edges have delay, and they also have a capacity, how much flow they can carry. And the agent is a pair SI-TI. So agent want to send some amount of flow from SI to TI. And so the total amount of flow that can be sent on an edge cannot exceed the capacity. Based on that, you will be restricted on how much flow you can send. And so you should think of edges as the goods here. And so in general, market equilibrium may not exist. You can easily construct examples where equilibrium does not exist. For the network setting, you can just imagine that if the amount required by agents is more than the capacity of the edges, there is not going to be any allocation that can satisfy all covering constraints. This is a very simple example. Even if all the covering constraints can be satisfied, there may not exist in equilibrium because of the budget constraints. Okay? So we have to assume something. If we assume that a strong feasibility condition, that is, suppose you take a subset of agents and give them some allocation which is not wasting any goods, then you can allocate the rest of the agents. It's a very kind of mild kind of feasibility condition. If we assume this, then we can show that the equilibrium exists. The proof is through Kakutani fixed point theorem. It doesn't directly follow from the existence of equilibrium for the classical results of Arrow-Debreu for existence of equilibrium, exactly because of the reason that this covering constraint thing is different from the classical models. The next is equilibrium computation. So even with the strong feasibility assumption, the problem is PPAD hard. You don't know how to compute it in polynomial time. So we assume some more conditions. This is kind of a stronger type of feasibility condition which says that you take a subset of agents, give them their minimum cost allocation. So this cost has to be minimized aggregatively for this subset of agents. Then you can extend this allocation to the minimum cost allocation of all the agents. Okay, so this is a strong condition, I agree. But if we assume this, then we can compute the equilibrium in polynomial time, and this is what I want to talk about in today's talk, this algorithm. Okay? Good question. I don't know. But I can give you examples where this is, we know that this is satisfied. So we prove that for a number of settings, especially for the cloud market setting, it is satisfied for very general case like arbitrary arrival, arbitrary capacities, overtime, arbitrary number of goods, and so on. For the network flow case, if the network is series parallel, then this can be satisfied. But it's a good question whether if I give you a problem, can you check whether this condition is satisfied? Okay, so for the algorithm, if I, initially I thought that I'll give you the most general algorithm, but it was really messy and too many symbols. So I want to give you the basic idea and intuition behind the algorithm through the cloud market example. Okay. So for the cloud market, let's make things more formal. You have a set of agents who want to run these tasks, and there are a set of machines that they can use. The machines are available over time, okay? So our good is a machine comma slot, and we are going to divide the time into slots, say 1 hour slot, half an hour slot, whatever you want. Okay? A good is machine comma slot, and we are going to price the slots for every machine. Once you announce the price, as we saw, the agent is going to demand a good which minimizes cost. So what is the cost here? The obvious notion is a delay cost. So what is the delay cost of an allocation? So suppose an agent gets this machine in, say, slot 3, then it has to wait 3 slots to get that machine. So let's say the delay is 3 units for that allocation, okay? So let's say delay cost of slot T is T. This is just to simplify. You can put whatever number you want for every agent separately for the delay cost. Okay? And the second thing is whatever the allocation they demand will be within the budget, and it has to finish all the jobs. So the requirements of the job is defined by this Rij units of time on machine J. So they want to run these tasks, And we assume that, let's assume that they know that how much amount of machine they would need for every machine. And let's say Rij is this quantity for agent I and machine J. Okay? So for agent I, we have to allocate Rij unit of machine J, Rij amount like time, Rij amount of or Rij slots to agent I for machine J. Okay. So more formally about the equilibrium, once we announce the prices, the agent will say demand Fijt. This is one symbol we have to kind of remember. Fijt is the amount of good J, machine J agent I demands in slot T. Okay. It has to satisfy the covering constraint, right? First thing, the total amount demanded has to be, for the machine J, has to be at least Rij. It should be within the budget. If this is the demand for machine J in slot T, then this is the, if PJT is the price per unit, then this is the amount it has to pay for this allocation. And so over all machines and all slots, if we sum them up, then it should be at most the budget. And it should minimize the delay cost. So we remember the delay in slot T is T per unit. So the total delay in slot T is T times Fijt. And this is the total delay overall of the all of the allocation. So essentially this kind of defines the LP. You want to minimize the delay cost subject to these two linear constraints and non-negativity on Fijts. So this defines the LP to compute the optimal bundle, if you want to say optimal, for agent I, given prices. So if the prices are not known, then this is a quadratic program. But if the prices are known, then this is a linear program. And at equilibrium, the aggregate demand of, so let's assume that every, just for simplicity, that every machine is available of 1 unit in every time slot. Then the aggregate demand in a machine comma slot should be at most 1. And if it is less than 1, then the price should be 0. This is the equilibrium condition. So every agent should get a bundle which is the optimizer of this LP, and these market clearing conditions should be satisfied. This is the equilibrium. This defines the equilibrium. Okay, questions? Okay. So let's characterize the equilibrium before we move on to the algorithm. This will be crucial for the algorithm. So for any good J, first thing to observe is that as the time passes by, the delay cost is more and more. So the later slots cannot be priced higher because nobody is going to buy if you price them higher, right? They are free to choose whatever slot they want. Okay. So the prices has to be decreasing. The second thing we can show is that the difference in prices has to be also decreasing. Okay. If this does not happen, then, so suppose we have one agent, 3 slots. The agent wants only 1 unit of the slot, and it has, say, $4. Let's say we price them to 640. So the prices are not decreasing. It's 2, and then the difference is 2 first, and then 4. Now suppose the agent demands second slot. It has $4. Then the delay cost is 2, right? But if it demands 2/3 of first and 1/3 of the last, then it can afford the bundle, right? But the delay cost is 2/3 plus 1, which is less than 2. So essentially, wherever there is a kink, so there was a decreasing, and then they start increasing, that slot will not be sold, basically. So if you're pricing it non-zero, then it's not an equilibrium. So this is not going to happen. Basically at equilibrium, the difference in prices will have to be decreasing. So if we put both of these things together for a good, the prices have to be decreasing and difference in prices has to be decreasing. So it's piecewise linear convex curve. So for every good, we essentially have to find this piecewise linear convex curve. And now let's look at what will the allocation look like at the optimal bundle. So the agent is experiencing 2 types of cost, delay cost and the monetary cost. When you write the KKT condition for the LP, optimal bundle LP, you will get this term in the dual. Okay? This is combining, here lambda I is the dual variable of the budget constraint. It is combining the delay cost and the monetary cost, and lambda I kind of defines the convergence rate between delay cost and monetary cost. And when you write the condition, it essentially is trying to minimize this, let's call this perceived cost. Okay? So it will buy only those slots where this perceived cost is minimized. But you can compute the perceived cost only when lambda I is given. Right? So that's a variable, that's an unknown. But this is still telling us something. So first thing, lambda I is common across goods and across slots. Okay? And it buys this slot only if this value is minimum. From this, we can immediately prove that if an agent is buying multiple slots of the same good, then those slots have to be part of the same segment, and the slope of the segment has to be minus lambda I. I'm just writing lambda I to be not make things confusing, but this is a negative slope, and it will be minus lambda I. Okay? Because suppose you're buying t and t prime, then this quantity for t and t prime should be equal, and from there you can get that the price difference has to be lambda I times t prime minus t. Quite a lot of work in scheduling and pricing, but what exactly? So they don't care about market clearing. Mainly, probably they care about social welfare maximization or profit maximization. But when we put this market clearing, things completely change. So if putting everything that we saw together, the price curve for a particular good has to be piecewise linear convex and decreasing. If the total number of slots required by all the agents is k, then k plus 1 good will be 0 priced. And for a particular agent, the assignment, the allocation will be in a single segment. And the slope of the segment has to be lambda I, the dual variable of that agent. This essentially defines optimal bundle. For the market clearing, if we take, so this property tells us that for every segment, there is a set of agents who are allocated to that segment. So we can talk about the set of agents allocated to a segment, right? For a segment, if we look at that set of agents, and let's say Lj is the requirement, total requirement of all of these agents for this good, then market clearing says that the total money of these agents should be exactly equal to the total price of these slots, Lj slots, right? Okay, so this is kind of putting all the properties of equilibrium in one slide. Now, how do you, when we try to approach computation of any problem, first thing we try to look for is whether the set is convex. So remember, we are not even trying approximation, we want exact equilibrium. Okay? And so initially we didn't care, and we just tried to get an algorithm, we failed, and then it struck, is it really hard? Maybe we should try to prove it hard. And the first thing we could kind of show was that equilibrium prices and allocation are non-convex. This is a kind of a two-dimensional picture of a six-dimensional picture, which is an unfair thing, but the gray area, so these points are points, the dots are points in the sixth dimension, and this gray area is kind of the convex hull of the points that they are connecting. And the white, so the gray area and the lines and the points are equilibrium, but the white part is not equilibrium. Okay, so it's not easy to comprehend because it's a two-dimensional projection of a six-dimensional object, but essentially I want to kind of convey that the equilibrium is highly non-convex. It looks something like this. We couldn't construct an example where it is disconnected completely, but there may be a case where equilibria in general could be disconnected. Sorry? Yeah, the lines are also equilibria. Yeah. Okay, so for the algorithm, let's me focus on a single good, and that too for a single, every agent just requires, say, a single slot, okay? The market that is constructed for the hardness proof does not satisfy the extensibility condition. I didn't kind of, so for this market, cloud market that I described, extensibility is satisfied. Under mild assumption that the later slots have more delay. It should be just, the delay should be monotonic across over time. It need not be t plus 1 and so on, but it has to be monotonic. Then it is extensible. Yeah, I didn't give you a proof, but it is. Okay, so the algorithm has to construct this piecewise linear. So for now we'll forget about the allocation. Let's just first construct the price curve. Okay, so it is piecewise linear convex curve, and we are going to construct it bottom up. So we'll first construct the last segment, second last, and so on. So for the segment, we saw that the only two things are required. One is its slope, and second is who all are allocated to that segment, the set of agents allocated to this segment. So let's call the slope of this last segment lambda star, and the agents allocated S star. We don't know either of these quantities. We have to find out both of these quantities. Okay, so for the market clearing, we know that the total money of these agents should be exactly equal to the total price of these slots. The price of the slots, it starts from 0, and it is a linear segment, so it's lambda star, 2 lambda star, and so on up to size of S star lambda star from bottom to top. Okay. So the total price is this. If we simplify, we get this summation of 1, 2 up to size of S star. Let's call it sigma S star. It is basically size of S star times size of S star plus 1 divided by 2. So lambda star from this expression, we know that is summation of money divided by sigma S star. Right? Let's define this term, and we don't know either lambda star or S star, but if we know S star, we can compute lambda star from this expression. So let's define lambda S for any set S to be this quantity, the same, the money divided by sigma S. Now remember, the last segment has the lowest slope once you discard the negative term, negative sign, right? So for any other set, the lambda S will be higher than lambda S star. Okay? So essentially, you're trying to find a set S star where this lambda S is minimum. But there are exponentially many sets, and we don't know how to do this minimization like directly. This is not a submodular function. So then, so far we have this. Expression summation of money for the set divided by sigma S is lambda S, and it is at least lambda star. So now focus on this inequality, okay, and simplify it. So we get that for every set S, this expression is non-negative, and it is exactly 0 when S is S star. So essentially, to find S star given lambda star is just finding this arg min of this expression. This is a submodular function given lambda star. Okay, so now we can do we can find this minimum in polynomial time. There was another way to so previously we could given S star we could compute lambda star. Now it's other way around. Given lambda star we can compute corresponding S star. Okay, this is more powerful. Okay, so now, but then how to find lambda star? And you can guess binary search. Okay, so let's call this function the minimum value of this expression given lambda star, g lambda star. This value is 0 when lambda is lambda star. If lambda is less than lambda star, then this is great. So this expression, if you simplify, you can see that it will always be positive. Right? So G lambda will be positive in this case. And so for every lambda which is less than lambda star, G lambda is positive. For every lambda which is greater than lambda star, so for the set S star, this expression will have to be negative for every lambda which is greater than lambda star. Right? Just simplification of this expression shows you that you bring this sigma lambda star S star here and bring it that side, then this expression is negative. So the minimum value for this lambda, basically G lambda will be negative for every lambda which is greater than lambda star. So if we plot everything based on this observations, we get that the G function will look like something like this, which is even not kind of going as oscillating. It is positive for lambda less than lambda star, negative for lambda more than lambda star, and then we can just compute it using binary search. Every round of binary search will have to do some modular optimization. This is okay. So this essentially completes the algorithm because once we find the last segment, we can just repeat that procedure. Once we find the last segment, we know all the agents that are allocated, remove them, and all the slots that are allocated, their prices we know. Only the exact allocation remains, but we show that the property of the price is such that the allocation will always exist. So, and for the last segment which is allocated, we know the price, and we can then, instead of the 0 price, you start at the price, whatever was the price of the last segment, and you can repeat the procedure. Let's say now you want to compute the second last segment, whose slope and set you don't know, and we can just repeat this procedure. Okay. So, any questions on this? Yeah. Exactly, yeah. So this kind of, I give you a very high level idea of what's happening in the general market. Actually, it extends to the most general market, which can have multiple goods, arbitrary requirements for each goods, arbitrary capacities of each goods across slots, arbitrary arrival of agents across time. That was the first point I made, that the lambda is the dual variable, the budget constraint. So it's common across goods, across slots. So there is some correlation among the prices across goods, and that is required for, in the general case, proving that there exists an allocation. So here I didn't talk about what will be the final allocation, right? I just gave you how to compute the price. Right? We also have to decide final allocation, and we'll have to prove that there exists an allocation which can satisfy everybody's requirement in that set S star. Yeah. Once you have the prices, it's an LP, but why that LP is feasible? The budget constraints will be satisfied, but why the exact requirements will have to be satisfied. So yeah, okay, I didn't kind of mention, but those two conditions are not exactly a subset of each other. Extensibility and strong feasibility. Be much simpler algorithm for this. This may sound like yeah, like that. But when you go to the most general setting, things are much more complex, and you really have to kind of, when you allow any arbitrary delays and arbitrary covering constraints, I don't see how it may be simpler. It will be really interesting to see if it is really simple than the most general scenario. Okay, so overall, like, you repeat this procedure of constructing segments from bottom up. For the general market, every step is much more complex, as you can imagine. There are no time, there are no slots as such, right? There are just goods. People just have covering constraints over goods. The covering constraints could be arbitrary, they need not be just do you want some specific amount of goods. It need not be like that. In fact, for the flow problem, you can have negative signs in the coefficients. So in that sense, it's not that simple. Like if you try to write the covering constraints only with the positive signs, then you will have exponentially many constraints because you'll have to write it in terms of paths. If you really want to write it in terms of like just incoming flow equals outgoing flow at every node, then you will have to have some negative signs there. So things become much more complicated. The lambda, essentially what happens is the lambda is will still remain the dual variable of the budget constraint, but now we will get some kind of a parameterized LP that we'll have to deal with. And the dual of that LP will give you the prices. And now you should think of the segments as only the set and not across any time or like that. Just the set of agents who have the same lambda that defines a segment. And we will kind of try to fix these segments. As you fix the segment, you kind of also setting the price of the goods that they are buying. So you will have to maintain those prices. You cannot change those prices in the dual. So as you kind of manipulate these lambdas, so the way we do it is like you fix the lambdas of the agents who have the minimum dual variable. That is your first or say last segment. You set the prices of the goods that they are going to buy. And now the prices of these goods cannot be changed, okay? And the rest of the price for the rest of the goods, the prices will have to increase, and so on. So there are these major challenges to kind of extend this algorithm to the most general case, which is kind of you have to maintain the monotonicity of the prices, you have to maintain the payments of the agents that you have fixed for the previous segments, and finally, after all of these, you will have to prove that the allocation exists, and this really becomes non-trivial for the general case. Okay. In terms of the scheduling market, as I already said, I showed you the algorithm only for single good and one slot per agent, but it extends to the most general setting, which is multiple goods, arbitrary requirements, arbitrary delays, arrivals, arbitrary capacities, and so on. The market being market, it satisfies a number of fairness properties. The allocation is always Pareto optimal in terms of the delay. So there is no allocation which can decrease the delay of all the agents. It is envy free. That is, if everybody has the same budget, then nobody wants anybody else's allocation. Everybody likes their own allocation more than anybody else's allocation. This envy freeness. It satisfies something called fair share. That means, suppose I give every agent every good which is proportional to its money, then it likes its own allocation more than this allocation. If we think of this market as a mechanism, or this algorithm as a mechanism for this market, for the clouds, for the scheduling part only, then it is truthful. So imagine that can agents lie about their money or their RIJs? And no, they cannot gain by lying about these parameters. Another setting people generally consider in economics is quasi-linear. So one criticism could be like agents may not only want to minimize delay, but they may also want to minimize their payment, okay? Then you can consider a quasi-linear setting, which is minimize the agents when they decide what they want to buy, they minimize delay cost plus eta times payment. We show that there does not exist any truthful Pareto optimal anonymous auction. Anonymous auction is like if two agents have same constraints and same money, the mechanism should not differentiate between them. In this case, so there is no such mechanism, and we use a previous result of Dubzinski, Levy, and Nisheeth for this construction. There are a number of open problems in this setting. One is to identify more subclasses of the most general market for efficient algorithm. What about online setting? Here we assume that all the agents come upfront and all their money, parameters, everything, or covering constraints are not known upfront. But what if they are not known? We assume that the goods are discrete, but what if the goods are, divisible, but what if the goods are discrete? That means in the scheduling setting, suppose the agent says that I want suppose I want 2 hours of this machine, but it should be uninterrupted and complete. I don't want to share that machine at all with any other job at that time. Then what can be done? And you can think of many more settings because scheduling is classical problem and there are a lot of settings here. In this market setting, I don't know of any result. This is a very recent result. It will appear soon. Yeah, so kind of that's what the second theorem was, right? So if they care about saving money, they may want to lie. In the original model, we just assume that they have some budget and just they care about minimizing the delay. So in this setting, there is no truthful mechanism. And that's it.